5.4, the fundamental theorem of calculus. So I'm just going to read through this introduction, and then in the next slide when we see an illustration, it's much easier to understand what's going on, but obviously this is a very important theorem since it's called the fundamental theorem of calculus. It provides the bridge between two seemingly unrelated branches of calculus: differential calculus, which arose from the tangent problem, and integral calculus, which arose from the area problem. In sum, the fundamental theorem of calculus gives the precise inverse relationship between these two, how to get forwards and backwards between the derivative and the integral, pretty much. The first part of the fundamental theorem of calculus deals with functions of the form g of x equals integral from a to x of f of t dt, where f is a continuous function on the interval from a to b and x varies between a and b. So now what we're saying is we're going from a, which is a point, to some other point, which is a variable. X is a variable, and that is the key here. It's a variable that is somewhere between a and b. Note that g depends only on x, not on t. And we're saying, let's take the integral of f of t dt, where the function depends on t. But we're saying, let's let g of x be some accumulator function, and I'll talk more about what I mean by the accumulator function, from a to x. If f happens to be a positive function, then g of x can be interpreted as the area under the graph of f from a to x, and x is between a and b. Thus, g is the area so far function, and I like to call it the accumulator function because as x gets bigger, the area gets larger. If f is the function shown below, and g of x equals the integral from a to x of f of t dt, find the values of all the following. We know that g of x is this accumulator function. And so g of 0 is just going to be, let's stick in a 0 wherever we see an x. So we can let a be anything just so long that it's smaller or equal to our x. So let's, for this example, let's let a equal 0. Since 0 is the smallest thing we see here. And so the integral from 0 to 0, what is the area under the curve from 0 to 0? Well, that's just 0. G of 1 is just going to be the integral from, we're saying a is 0 to 1. So what is the area under the curve from 0 to 1? That's what this is asking. And so this area here, it's just a triangle, 1/2 base times the height. It's just going to be 1. G of 2 is the area under the curve from 0 to 2. So just more formally, isn't that just the area under the curve from 0 to 1? Which we just found, plus the area under the curve from 1 to 2. Add up this area plus this area, which is what I'm showing that I'm doing here. And this area is the base times the height. So that's just 3. and then g of 3 okay, I'm going to go 0 to 1 plus 1 to 2 since I already found those, plus the area under the curve from 2 to 3. Now, in order to find this area, I'm going to need to use an approximation. I don't know it exactly. And so, since these boxes all have an area of 1, I'm just going to approximate, it's like 1 and a little bit more. So I'm going to say this is about 1.3, this area, just approximating it. So I'm going to say that's 1 plus 2 plus 1.3, 4.3. Again, that's an approximation. I'm just going to move up here since I'm running out of room. To find g of 4, how am I going to do g of 4? G of 4 is the area under the curve unto this point. So in order to find that, what am I going to do? I'm going to do g of 3, which was this whole region here, and then I'm going to subtract out the area under this curve. And what is that area about? Well, that's about 1.3 also. I'm going to just approximate it at 1.3. But I need to subtract it because it was under the x-axis. And so that's going to leave me with 3. And then g of 5 is just whatever g of 4 was, because that brings me to this point, and then I have to subtract. If I said this was 1.3, this looks pretty symmetric, so that's 1.3 also. I have to subtract 1.3 again. And the reason is g of 4 is giving me the area under the curve up until here. And then this area is again negative. This is a negative, and this is a negative because they're below the x-axis. So I get 1.7. Example 2 says g of x equals the integral from a to x of f of t dt, where a equals 1 and f of t equals t squared. Find a formula for g of x and calculate g prime of x. All right. G of x equals the integral from a to x of f of t dt. A is 1. And f of t is t squared. So the formula for g of x is that so far. And so what is this? Okay, it's saying take the antiderivative with the variable being t. So the antiderivative is 1/3 t cubed. Nothing fancy. This is the variable. We're taking the antiderivative with respect to that variable. We're going to evaluate this between 1 and x. So I get 1/3 x cubed minus 1/3 times 1 cubed. In other words, I get 1/3 x cubed minus 1/3. So that's what g of x equals. Then I just find g prime of x using my good old-fashioned power rule. So 1/3 times 3 is 1, x, subtract 1 squared, minus 0. So the derivative is just x squared. In general, if g of x equals the integral from a to x of f of t dt, where f is a continuous function with f of x always greater than or equal to 0, meaning that my graph is always above the x-axis, then g of x can be interpreted as the area under the graph of f from a to x. And again, I just call this the accumulator function because as x gets greater, I'm accumulating more and more area. So the first part of the fundamental theorem of calculus says that if we have g of x equal the integral from a to x of f of t dt, okay, then the derivative of the antiderivative is just the function itself evaluated at x. In Leibniz notation, we can say that the derivative of the antiderivative is the function itself evaluated at wherever we have accumulated up until. I like to think of it like this. It's a little proof for myself. G of x is the antiderivative from a to x of f of t dt, which means the antiderivative of f of t is big F of t, right? And I want to evaluate that from a to x. And then I'm just using my evaluation theorem, just stick in an x, f of x, minus f of a. Now this is saying something about the derivative. G prime of x is f prime of x minus f prime of a. Now the derivative of big F is just little f. A was a constant. So big F of a is going to be a constant. It's just a number. And so this derivative is 0. And that is why the function depends only on whatever we're accumulating it until. This is very, very important, and we're going to be talking a lot more about it. So it takes us to our next example where it's saying find g prime. Well, g prime of x, in this case, we know f of t is the square root of 1 plus t squared. So, from the fundamental theorem of calculus, g prime of x is just f of x. That's it. Yes, you must have an x here because we need to evaluate it at whatever x we're at. We don't need to worry about this number. It doesn't matter what it was. It could have been a 5. It could have been a -2. It doesn't matter what it was because at the end of the day that drops off when we're taking the derivative. So this is saying find the derivative of the antiderivative of secant of t. Alright, so what we need to do here, and this is a very good example of a problem we will see, that we can't just say, alright, f of t is secant t, and so g prime of x is just going to be f of x. And the reason is because I said that worked if we were going from some a to an x, but I'm not going to x, I'm going to x to the 4th. So, in order to do this, I'm going to need to apply a chain rule. First, I'm going to evaluate it. At wherever I am. So I'm just doing f of x to the 4th. And then I need to chain wherever I'm going to. So again, I can prove this to you. Let's go back and use the same example. So let's just go from a to x to the 4th now. And just like we did before, the antiderivative of little f is big F. Evaluate it from a to x to the 4th. And I would just get f of x to the 4th minus f of a, and then the derivative is just going to be the derivative of this guy. Alright, here's my baby. So I take the derivative, leave the baby inside, and then I have to chain it. minus f prime of a. Again, a is a constant, so this is a constant. The derivative is 0. The derivative of big F is just little f. So that's my proof. We're going to be using that a lot. There are two parts to the fundamental theorem of calculus. We've covered part 1, and the second part is just saying that the antiderivative of little f is just big F of b minus big F of a, where f is any antiderivative of f, that is big F prime is little f. Taken together, these two parts of the fundamental theorem of calculus say that differentiation and integration are inverse processes, and each undoes what the other does. And that is very, very key. It might sound minor, but it is very key. And so that's the end of this lesson. We'll be seeing a lot more of it, of course.